that, here's today's agenda. Our speakers today are joining us from the UK and from Greece. So shout out to you across Europe. Eleni Iacovidou is a senior lecturer at Brunel University in London in the UK, and her research focuses on holistic sustainability assessments of resources and waste management systems in particular to support strategic and innovative decision-making. And Eleni is a chemist by training. Our second speaker is Olwenn Martin. She's also a chemist by training. And Olwenn's expertise lies in systematic review and meta-analysis and socioeconomic analysis, as well as in the integration and translation of scientific evidence into policy. And Olwenn actually quite recently joined University College of London as lead personal tutor for health and environment. So congratulations on your new job, Olwenn. Further, Olwenn is also on the management board of the European Chemicals Agency, ECHA. And then last, but by no means least, we have Loula Gerasimidou. She is an environmental engineer by training, and her expertise is in solid waste management methods and in analytical techniques of waste characterization. And currently she's a research fellow at Brunel University, London in the UK, with a focus on systematic evidence mapping and qualitative and or quantitative sustainability assessments of resources and waste management systems across their entire life cycle. Loula has research experience on plastic packaging systems, including, and that's what we will get into today, challenges and trade-offs related to the transition towards a circular economy. So as you can see, we're in good hands with these scientists today, and I'm really also looking forward to hearing perspectives from participants in the audience today. So we'll get to all of that then once we've concluded the presentations. And now over to you, Eleni.
Thank you, Jane, for the introduction, and thank you to all in the Food Packaging Forum for this excellent collaboration. We're really happy that we have the work with you and that we are doing this webinar, which I hope that our participants are going to enjoy. Now, Loula is going to share her screen and she's going to advance the slides. So Loula, thank you. So our presentation is on the chemical migration and on the polyethylene terephthalate, also known as PET or PET. We call it PET, just so you know, and the implications that this may have on circularity. So next slide, please. So you may wonder why we wanted to focus on PET, because PET is the most widely used type of plastic used by the beverage industry for the containment of drinks, such as carbonated drinks, soft drinks, fruit juices, and beers. And not surprisingly so, because PET offers a unique set of properties. It has good moisture barrier, it has high transparency, high reflectiveness, it's easily processable, and it is also economically affordable. It has a very low price. And so this has led to the use of PET quite widely. And it's now considered to be a single-use plastic item with a short shelf life, which is around 6 months. And though this supports the on-the-go consumption and the modern lifestyles that we currently lead, it also contributes to pollution. It's one of the most commonly found plastic litter items across the globe. And it's now recognized, plastic pollution is now recognized a planetary boundary challenge that we urgently need to address because of the negative impacts that plastic pollution has on the environment, but also on the economy and society. On the positive side, PET is regarded as a high value plastic that can be recycled in both an open loop and a closed loop fashion. Now, open loop recycling refers to the cascading use of PET in other applications, such as in fleece production, in the production of reusable shopping bags, in t-shirts, whereas the closed loop recycling refers to the use of PET in food contact materials such as drink bottles, as well as other food containers. Next slide, please. So in 2019, 58% of the PET bottles were collected and sorted for recycling across the UK and the EU. And this is because there are now measures, a wide variety of measures that promote a reduction in the plastic waste and an increase in the recycling of plastic waste. Now, the adoption of these regulatory changes and measures is going to increase the recycled content in plastic packaging, including PET drink bottles. And we've seen the directives at the European level, such as the directive on single-use plastics and the directive on packaging and packaging waste, demanding that change, as well as the EU packaging levy, which has a tax on non-recycled plastic packaging. And at the UK level, we have the targets of the UK Plastic Pact, and we also have the newly introduced plastic packaging tax that demands a 30% recycled content in all plastic packaging, including PET drink bottles. So whilst this adoption of new strategies and regulations is considered to be beneficial for promoting the circularity in the plastic packaging system, it also begs the question of whether we know enough about the impact of these strategies on food safety, and whether we actually are prepared to anticipate and mitigate the risks of such measures on the food safety. So next slide, please. In reality, we think that the increased use of recycled plastic could be concentrating and introducing potentially hazardous chemicals that could be migrating into food, and thus it could present a safety challenge that we need to address. This is not news, but now there is an increased amount of recycled content that is going to be introduced in the food packaging material. So we need to better understand what's happening. So even though we have European regulations on the food contact materials and articles at the stage of manufacturing and processing, as well as quality assurance requirements for recycling processes, and we have this union list that includes specific migration limits for intentionally added substances, also known as IS, and some specific, some threshold limits for non-intentionally added substances, known as NIS. These limits do not account for mixture effects, do not account for exposure by other routes, and also they are based on past toxicological studies, which means that if we want to inform a better circularity on the plastic packaging system, we need to gain an improved insight on both the IS and the NIS, and most importantly, we need to get an up-to-date analytical standard for both of these categories. We need to acknowledge the likelihood or that these compounds, the IS and the NIS, could be present in the packaging, in the recycled PET, also known as rPET, and therefore a better insight would help us to inform the manufacturing industry so that they can improve the safety standards for the food contact materials and the PET beverage bottle specifically. So next slide, please. So given the scale of recycling ambitions that we currently have at the UK and the European level, we believe that we need to gain a better understanding of the food contact chemicals that could be migrating from PET and rPET, and we need to do so across the entire life cycle of the PET drinks bottle. And this could help us to understand at which stages of the bottle's life cycle could be more prone to contamination and try to introduce measures by which we can prevent that and mitigate the safety risk. So our work focused on two strands. The first one will look into the food contact chemicals found in PET and rPET, which may have exceeded the current specific migration limits under specific text conditions at least once. And we also looked at those that were most frequently analyzed in order to understand the underpinnings behind that. And we also looked into the influential factors, practices, and conditions across the entire life cycle of the PET beverage bottles in order to understand which may affect and or control the presence of IS and NIS. And I will now give the word to Dr. Martin to explain the methodological approach we adopted in order to carry out this analysis. Thank you.
Thank you, Eleni. So I will briefly describe the where we got our data from. And this is part of a wider project that was a systematic evidence map of what we know about chemicals can migrate from food contact materials into food or be extracted from food contact materials. We adopted this systematic evidence map methodology, which is closely related to a systematic review method. Systematic evidence maps generally allow to answer broader research questions, as was the case here. And the one step that is missed compared to a systematic review is that we did not carry out a detailed critical appraisal of the studies that were included. So we searched the literature that included 5 different literature databases, included PubMed, Web of Science, Scopus, Google Scholar, and Science Direct. We also searched the grey literature, including databases such as Environa, OpenGrey, and Core, in addition to manual searches to specific institutional websites. The search strategy for the literature databases included 109, a combination of 109 search terms. And that led to initial stage once we removed the duplicate of nearly 16,000 individual records. These were screened for eligibility, and as part of this screening process, there was a stage where we also looked at the confidence we had in the chemical identity of the chemicals that were being analyzed. And that, so first we scanned the title and abstract for eligibility. That led us to nearly 3,000 records, and that was whittled down once we looked at the full text screening to 1,210 records. That's 1,210 papers. We extracted the data with the help of a bespoke semi-automated tool to help us do that. And then that was process that data. That led to 22,522 database entries for a total of 2,881 food contact chemicals that were detected. I've included the QR code. There's the one on the slide just before. The protocol, the detailed protocol for the systematic evidence map is publicly available. It was published prior to completing the work on the website Xenado, and with this QR code, you'll be able to find the entire protocol. So that forms FCC MyJEX, which was part of a different webinar. And here I've also included the QR code for the database that's hosted by Food Packaging Forum, which allows you to sort of explore the entire database. So from this larger set of data, we specifically look at a smaller subset that was concerned with PET. So we specifically looked at the records that describe the migration from PET or recycled PET articles, such as films, bags, containers, bottles. But we then excluded any extraction experiments are not included in our work, or anything that's not associated with drink bottles or precursors. So PET pellets or flakes were included in that. That led to over 1,000 migration tests from about 91 studies specifically looking at PET. And the next slide is simply comparing what we found when we looked at FCC MIGEX generally, not just for PET, compared to another previous work that had been done, which is called the FCC-DB, the Food Contact Chemical Database, which is a compilation of all the chemicals that are authorized for use worldwide. And one of the interesting findings from FCC MIGEX was that about 65% of the chemicals that were detected, that had been detected as being potentially able to migrate from food, so that's migrating or extracted from food contact materials, were actually not listed for use. So that's a few words about the methodology, and now I will pass on the floor to Loula, who will give more detailed results about PET in particular.
Thank you, Olwenn. So, so moving to the results. We can see here a global map that shows the total number of studies that have conducted migration experiments on PET beverage bottles, including both virgin and recycled PET samples. As Olwenn mentioned before, we found in total 91 studies that carried out migration experiments. And most of these studies were carried out in Spain, Germany, and China, as we can see. So we collected all these chemicals from these studies, and we grouped them into 6 types of food contact chemicals. We have catalysts, monomers, and additives, which are considered intentionally added substances. And we have also degradation products, oligomers, and residual contaminants, which are considered as non-intentionally added substances. The catalysts are used to regulate the incorporation of monomers into the polymer chain. The monomers are the main components that build up the polymer chain. The additives are used to achieve a desired technological effect. The degradation products are breakdown products coming from the degradation of polymers and additives due to high temperatures and or irradiation energies. We have the oligomers, which are intermediates of the polymerization processes, and the residual contaminants, which are actually undesirable substances accompanied by the raw material and the equipment. So according to this grouping, in this pie chart, we can see the proportion of each type of food contact chemical in the total number of food contact chemicals that have been detected to migrate from PET bottles into their content. So we can see that 41% of the total detected food contact chemicals are residual contaminants, followed by degradation products, which represent the 25% of the total number of detected chemicals. So we can see that the vast majority of chemicals that migrate from PET bottles are non-intentionally added substances. And this can also be seen by this graph that shows the number of chemicals that have been measured by researchers and how many of them have been detected to migrate at least once, including also the number of studies. So if we take as an example the additives, we can see that 19 studies measured the migration of 34 additives, of which 24 were found to migrate at detectable levels at least once. So in total, we found 193 chemicals that have been measured. And from these, 150 have been detected to migrate from PET bottles into their content. And from these 150 chemicals, 113 are non-intentionally added substances, and only 37 of them are intentionally In addition to this, we checked how many of the chemicals that we found in our systematic evidence map have been included in two databases that are related to chemicals. We have the food contact chemical database, as Olwenn presented before, and the chemicals associated with plastic packaging. We can see that most of the chemicals that we found in our evidence map are included in both databases. Still, there is a considerable number of chemicals, more than 40 chemicals that have not been included. And this shows actually the lack of data traceability. And we can also see how many of the chemicals that we have found are related to PET according to these databases. And we can see that this number is very low. And this is because that both databases are not able to provide a comprehensive and polymer-specific detailed information. In addition to this, among the detected food contact chemicals, we identified how many of them have exceeded the regulatory limits at least once. And when we say regulatory limits, we mean the specific migration limit for chemicals that are included in the union list, or the threshold value of 10 microgram per kilo if these substances are not included in the list. So we found in total 18 substances that exceeded the migration at least once, and we grouped these chemicals according to the type of food contact chemical and the stage of PET bottles life cycle. So we can see that most of the chemicals that migrated and exceeded the limits can be found at the stage of production and distribution, storage and distribution. And this is because most of the researchers have focused on these two studies, while there is very limited evidence at the stage of reuse and reprocessing. In addition, we included the geographical origin from which the analyzed PET bottles were purchased. And we can see that the chemicals that exceeded the migration and we can see that the migration of these chemicals was found from bottles that were purchased around the world. In addition, we wanted to see which chemicals have received an increased attention by researchers. And we found that the most highly investigated chemical is antimony, which is an intentionally added substance that is used as catalyst in the form of antimony trioxide. And in the first graph here, we can see some box plots that show the variability of antimony migration at each stage of PET bottles life cycle. We need to mention here that these box plots are used just to present the variability of antimony migration at each stage, and then a comparison among the stages is not recommended because the analytical techniques and the migration conditions that have selected might differ from study to study. The second most highly investigated chemical is acetaldehyde, which is not expected to be found in PET bottles, but it can be present as a thermal degradation byproduct at the stage of preform production. And in these two graphs, we can see some box plots that show the variability of acetaldehyde migration from PET bottles into still water and carbonated water. Literature evidence reported that there is a positive correlation between the migration of acetaldehyde and the water saturation with CO2 gas. And this is because of the pressure that is caused by the CO2 gas rather than the CO2 on itself. Finally, endocrine disrupting chemicals have received increased research attention, with the most prevalent being some specific phthalates and bisphenol A. An interesting finding here is that for these EDCs, the frequency of detection is very high. In some cases, might be more than 90%. And this means that these chemicals, these EDCs, are commonly present in PET bottles. As a second part of our result, we collected all studies that determine the migration of chemicals from PET bottles into their content at each stage of PET bottles life cycles. So at the stage of production, we can see with this color ranking system, the research attention expressed as the number of studies for all types of food contact chemicals. We can see that there is very high research attention to residual contaminants. For the catalyst and degradation products, the research attention, we characterize it as moderate. The number of studies is between 11 and 15. We have limited attention for additives and oligomers, and very limited for monomers. So according to these studies, we found the most influential factors on the migration of food contact chemicals at the stage of production. The first factor is the place of production, and this is because the quality assurance measures at the stage of processing, the physical properties of the PET bottles, the plastic trading, and the operating conditions at the stage of manufacturing might differ considerably from region to region. A second factor is the bottle capacity. There is a positive correlation between the migration of chemicals and the ratio of surface area to water volume. This means that the migration of chemicals is higher in small bottles compared to large bottles. We have also the thickness of the bottle wall. The higher the thickness, the higher the migration. And there is another controversial factor, which is the color of PET bottles. There are some studies that reported considerably higher migration in color bottles compared to clear bottles, while others have reported that there is no significant difference. At the stage of storage and distribution, we can see again that there is high attention for the migration of residual contaminants and catalysts, limited attention for the additives and degradation products, and very limited for monomers, while we didn't find any study for the migration of oligomers at the stage of storage. According to these studies, the most influential factors are storage temperature, storage time, and UV exposure. All these storage conditions have a positive correlation with the migration of chemicals, although the level at which these conditions affect the migration depends on the chemical. For example, the UV exposure has been reported that affects mostly the migration of acetaldehyde, while the storage temperature affects mostly the migration of antimony. In any case, extreme storage conditions are not recommended and should be avoided. We have the stage of reuse. At this stage, as we can see, there is very limited attention to the migration of chemicals. The most influential factors at this stage is the frequency of reuse, which means the number of times that a bottle has been reused by the consumer, and the extent of misuse by consumer, which is typically filling the bottles with highly acidic or fatty foodstuff under uncontrolled conditions. It's worthwhile to mention here that these conditions at the stage of reuse might be more influential than the storage condition in some cases. And this indicates that we need to pay special attention at this stage in the future. And finally, we have the stage of reprocessing. Again, at this stage, there is very limited attention. However, the most influential factors, according to the evidence that we found, is the level of cross-contamination of post-consumer PET bottles. And the level of cross-contamination depends, firstly, on the design components of the post-consumer bottles, including labels, inks, and adhesives. It is affected by the collection system. The curbside collection system, for example, increases the level of cross-contamination compared to the deposit return schemes that promote the bottle-to-bottle recycling. And of course, it depends on the waste stream in which post-consumer PET bottles are disposed. The other two factors are related to the technological performance of the reprocessing infrastructure. The first is the cleaning process. According to the literature, the conventional cleaning process provides lower decontamination efficiency compared to the super cleaning process. And at the moment, there are more than 40 commercially available decontamination technologies that consist of a combination of cleaning processes. And this leads to a variable decontamination efficiency and therefore quality of our PET, making quite difficult and challenging to define the optimum content of recycled PET from a safety perspective. And we have also the operating conditions at the stage of thermal reprocessing, since degradation products and oligomers might be formed at this stage. So in this, this is a graphical abstract that summarizes our main key findings. So to sum up, we found that 193 food contact chemicals have been measured by researchers that conducted migration experiments on PET beverage bottles. From these chemicals, 150 have been detected to migrate from PET bottles at least once. And only 41 of these detected chemicals have been included in the union list, are considered authorized substances, while the majority of the detected chemicals have not been included in the union list. The research attention was paid mainly to the migration of acetaldehyde, antimony, and some specific disease, and we can see the main influential factors at each stage of PET bottles life cycle. So at the production, we have the physical attributes of the bottle and the geographical origin. At the stage of storage, we have the storage conditions. At the stage of reuse, we have the consumer behavior. And at the stage of reprocessing, we have the decontamination efficiency and the innovation on waste management of post-consumer PET bottles. So now Eleni is going to present you the conclusions of our work.
Thank you, Loula. So in a nutshell, really, we looked into the safety and the quality of implications arising from reprocessing PET bottles. And we found that there is still lots of unknowns that we need to explore better in order to make some informed decisions about the use of recycled content. And this would help us to promote a more informed and sustainable circularity in the plastics packaging system. In relation to the food contact chemicals that we were found to be migrating from PET bottles, they could come from different geographical regions, which points to the fact that we might need to have better custom controls as to what kind of products we import in the European Union and the UK in order to better understand the type of PET bottles and other food packaging really that is returning back into our recycling system. And therefore, the lack of official guidance or risk assessment of NIAS, the safety and quality standards is an area where we need to put more work into in order to better account for these kind of changes in our system. And these are supported by monitoring and better insights into what we place on the market as well. So the third point is about the emphasis on the studies that we analyzed. There was too much emphasis on the antimony, aldehydes, phthalates, and BPA, which hinted to the fact that there is a bias influenced by the politics of bottled drinks manufacturing, and we don't mean that in a negative way. I mean, the beverage industry wants to make sure that the product delivered to the customers is up to the high standards, and they look for these substances because they affect the quality of the product, and it will affect the marketability of the product. And we understand how the businesses work, and we want to help them to become better and improve their insights about the food contact chemicals that could be migrating into food. So that leads us to our key recommendations, which is the next slide, about what we need to do. And this is across the entire plastic value chain. It looks into the production, the consumption, and the management. So at the production stage, we need to look into the design for recycling and the traceability principles in order to better understand how the labeling, the design of the bottles, as well as the traceability, because now electronic tracking is going to be mandatory in some places around Europe, is going to help us to better understand what happens in the system. At the same point, we need to understand how the production and the filling stage influence the food contact chemicals that could be migrating into food. At the consumption stage, we need to understand better the storage conditions and provide some kind of guidelines to the retailers, the small shop owners, as well as to the consumers, how to best store the bottles with the drinks, in order to prevent the migration of the food contact chemicals at that stage. And we also need to inform consumers about how the behavior change and their storage conditions could also affect what happens in the bottle. At the stage of the consumption, we also include disposal, because the disposal happens from the consumer. So they need to understand that if they want to help us promote this circular plastic economy, they need to dispose their plastic packaging in a more responsible manner. So we need to help the consumers on the go to try and find the deposit return schemes to dispose their empty bottles, so that we can make better use of them. But also in the household, they need to be trained and educated as to how to segregate their plastic waste in a more informed manner. And that will also improve the collection, the sorting, and the reprocessing ability of the PET drink bottles at the management stage. And at the management stage, we also need to understand what kind of technologies need to be adapted in order to ensure that the rPET is as clean and pure as possible, so that when it returns back to the production stage, the manufacturers can feel confident that this is a product of good quality that will not bear any kind of risks on food safety. And in order to do that, what we really need is a mechanism that will help us to transparently see and oversee the changes across the entire system, and to communicate more beneficial with one another. So communication amongst all stakeholders involved in the PET beverage bottles value chain is a key prerequisite for realizing the transition to a circular plastic economy, and to also make sure that this transition is safe for the consumers and for everyone. So these are the key messages that we wanted to deliver. Thank you for participating again, and we would like to open this to discussion. Thank
Wonderful.
you very much.
Thank you so much, Eleni, Loula, and Olwenn. Fabulous presentation. So we have time to discuss this now, and I see there's a couple of comments and questions in the chat already, most of them by Mike Neal. So Mike, you can get ready to unmute yourself and turn on your video in a sec. Just let me point out that I put a link in the chat where you can find the full study. The study is open access, so you should be able to download it there without any problems. And then also for everyone who joined us a little bit later, we are recording this webinar. We also will publish the recording of the webinar and the slides on our website shortly afterwards, next couple of days. So you can forward that to anyone who may have missed it today, or just go through everything again. And please, if you would like to ask a question now, you can raise your hand in Zoom. Or raise your hand in the chat, just say you want to speak. And everyone who has not renamed themselves, I kindly ask you to do so. Please just rename yourself in Zoom so that we know who is participating. You just put your name, surname, if you like, your affiliation. Wonderful. So with that, Mike, over to you. You had a comment and a question, I think.
Yeah, thank you, Jane. I wonder if maybe I could start by asking you to put up that last slide, the recommendation slide, and just let me talk to that for a minute.
Okay, you can also talk a bit shorter. Just
key
make your point.
Key actions that have been suggested. So the first one, adoption of design for recycling and traceability principles at the production stage. We've had this in operation in the PET manufacturing industry since the early 90s. The traceability of our production has been well and truly understood all along by, for instance, Coca-Cola, who can drop in at a moment's notice, quite literally a moment's notice, and check the production processes to make sure they're working properly.
So you think that this is not a key action that is needed, it's in place?
It's a key action that's in use already in the PET.
Okay, good.
We've been doing it
So
for
you
many years.
disagree with that point. Okay.
Monitoring the presence of chemicals at the PET production, PET bottles production and filling stage. As I'm sure you all know, that there is a requirement in the regulation for us to check NIS at every stage of the production. We actually do that. We measure it at virgin, we measure it at PET preforms, we measure it at bottle blowing, and we actually have in the industry an industry group that deals with this and are working at that. So that's actually already on the go. And I'm sure you'll know that when the new regulation, the recast regulation is published, there will be NIS data published by the PET industry and made available for the public to look at.
Great. So we ask the speakers?
Hang on. Let me finish, Jane. Come on, let me finish. Controlling the storage conditions that bottled drinks subject to. Every package of bottled drinks is set out with storage conditions attached to them. Promoting consumer behavior change. The PET industry has for many, many years, starting from the early 90s, asked consumers to collect the litter and bring it back in and to make sure that you recycle bottles. We had initiatives in schools way back as early as the 90s. And the difficulty with this is, as you know, consumers are very, very difficult to be helped. So improving the collection, sorting and reprocessing infrastructure of PET drink bottles and introducing traceability. We have been doing that since the early 90s. That is still working and still operating. It may not be public. I think perhaps there may be an issue there that we need to do something about the public aspect of this and make it more public. And I believe that's being done by Petco Europe.
Okay, Mike, final word.
Just a minute, there's two more.
One more minute.
two more things to finish off with.
Okay.
A compliance mechanism between a bilateral agreement which constitutes good quality rPET between the regulator and industry. You know quite well that the EFSA checks our quality of our recycled rPET, the rPET that goes out for sale, and without having good quality approvals from EFSA, we won't be listed in a regulation for use into that. And I can go in more detail on that. And then finally, revising the chemical risk assessment approaches used as a basis for setting the current regulatory limits. I agree with that. I think it's time that we stopped looking at what we put into PET, but what comes out. So the basis of 10/2011, frankly, should be removed.
Okay, good. So we have an agreement.
Nearly finished. Okay, and instead look at what actually comes out of PET. And if you look at virgin PET and recycle content virgin PET produced on virgin PET plants, the number of NIS present are around 0. There are oligomers, but there are full good quality risk assessments carried out on oligomers. And in terms of rPET, there are a number of NIS present in there, usually of the order of around 20. And all of those substances that are present are all fully risk assessed by industry before they go out and are subject to EFSA risk assessment too.
Wonderful. Thank you so much, Mike, for sharing your perspective. Who from the speakers would like to comment on that?
I have some questions,
Yeah,
but
just
also
hang
some
on,
comments.
please. We will just get to this, and I will, if you can rename yourself, please, in the meantime. Good. Eleni, go ahead, please.
Right. So, yeah, it feels like we have the answers on everything. We just, as researchers, don't know about these answers, apparently, which is it's such a shame, really. Maybe the industry can share with us a bit more about these insights on the design for recycling and traceability and the way they control the IS and the NIS at every stage of the plastics value chain. That would be great. So let's speak more with Mike in order to get these insights. In regards to the traceability, I want to say that Traceability, I'm not sure how it's been practiced by the industry at the moment. The way we mean it is about being able to trace and track what's happening on the bottle from the point of production up to the point where it returns back for reprocessing. And this is something that we don't currently have in the system. And if we do, then I don't understand why there's such vast amount of plastic bottles laying on the beaches and rivers and oceans of many countries around the world. And most of them come from Coca-Cola, for example. So maybe we need to try and understand what kind of language we speak. About the design for recycling, I think that there's something there that has been pushed by the EU and the UK here, that design for recycling may have not been incorporated when the bottles were initially being conceived and produced, because they are pushing a lot for design for recycling, making the bottles more easy to recycle, to remove contamination, which comes in the form of labels, which comes in the form of colors, of caps, of different glues and adhesives that are being used in the bottle. So I'm not sure if we have the answers there. I think that we need more research. And I think that these kind of views are widely acknowledged in the different spheres we engage with in the UK and the EU.
Great.
About the behavior of consumers, yes, okay. There's been some educational campaigns to inform consumers on how to dispose properly. Are we there yet? Don't we need more progress on that? We need to understand perhaps what's going wrong, because the consumers are still confused on how to dispose their packaging properly, including the bottles. There's been deposit return schemes implemented in European countries, and in some countries it works, in others it doesn't. So maybe we need to understand a little bit better what we have in our systems and the different contexts, how they come into the way of preventing this improved way of managing our plastic bottles.
Great.
Thank you.
Anything to add, Loula, Olwenn?
Just maybe a point on revising the chemical risk assessment. I think some work is ongoing as part of the chemical strategy for sustainability. There will be a one substance, one assessment approach as well. And in terms of sustainability, something I would like to stress as a chemical risk assessor or someone who looks at toxicology is these things are not static. So often we look back on limits that have been set, but if we want to be truly sustainable, we need to understand that scientific knowledge evolves and that some of these regulatory limits are also prone to change in the future. So some work in terms of understanding future scenarios in terms of what happens to these regulatory limits over a 30-year lifespan is important. The other important factor is mixture and mixture risk assessments.
Great, thanks a lot. It's obviously a complicated topic, but I'm grateful, Mike, for you sharing your perspective. And now we have, and apologize already, I don't know how to pronounce your name. I assume it's Greek.
Yeah, it's
Emmanuel. Yes,
Emmanuel. My name is Emmanuel.
European
Yes.
Food Safety Authority. So
Yes,
if you could make it brief, please, because we want to get to more people as well, please.
I won't take your time. Thank you for the presentation, really nice. I just have a comment about what Mike said about the methods that they are screening now in industry during the production of PET deniers. I'm really curious to hear what are the methods that they use to screen during the production of deniers. I'm working on this field of analysis and analytical chemistry mainly for 7 years, and to be honest, deniers is still a huge topic with a huge development that will be necessary to be done because changes in the regulation are coming. And in this case, now the requirements will involve some more data requirements from the regulatory point of view that need to be demonstrated and presented. Also, I would like to ask, because they mentioned in the beginning of the excellent presentation, Eleni and Loula, about the limited shelf life of PET. What do they mean? Because I think there was a comment, but I think the recycle of PET cannot be limited like polyolefins. So in this case, how they define this limitation on the shelf life of PET is, I'm really curious.
Okay, thank you, Emmanuel. So I think you and Mike can connect offline. There also was a comment by my colleague Justin, who was asking about the nice studies, Mike, that you referenced. So please, let's do that offline, not here. Eleni?
Yeah, about the life of the PET, we refer to the shelf life, how long it stays on the shelf of the supermarkets, the kiosks, the small shops, which is very short. It's very short. It's drink bottles are the highly consumed plastic good. So yeah, that's what we refer by short life, not the life time of the material itself.
Okay, thank you, Eleni. Loula, Olwenn, you just jump in if you want to.
Jane, can I just jump in on the shelf life?
Sorry, Mike. No, we've got Dorota waiting here. I apologize.
Well, the shelf life comment was wrong.
Dorota, you go ahead, please.
Thank you very much. Thank you. So first of all, I just want to congratulate on this study. What I actually very much appreciate that you not only point out to the problem, but also actually propose the key action to solve it. I think it's really very, very good if it comes from the scientists. My question is very short and direct. Maybe I didn't got it from the presentation, but how many of those chemicals were found to migrate as a mixture? So, I mean, how many of those chemicals were found simultaneously from certain samples? Thank you.
I think our analysis didn't really look at that specifically because there's no, I mean, specific study will focus on specific chemicals. So I don't think there is one study that is really doing that global assessment from PET at the moment. So this has to be understood to look at the data. It's not that all these 150 chemicals migrate from PET, from all PET all of the time. That's definitely not what we are saying. But you know, these are those that have been studied, that have been found to migrate at least once.
Yeah. I need to add here that all these actually are migration experiments around the world and are PET bottles that pertains worldwide. So these are individual studies that we collected and created a list of actually potential chemicals that can migrate from PET bottles according to the literature findings.
Yeah, and of course, one also has to keep in mind that many of these studies, I don't know exactly how many, maybe you know, Loula, were targeted studies. That means you find what you're looking for. There are few untargeted studies looking at migration from PET. So there may be more chemicals migrating. I just want to point out quickly, and I apologize, Mike, that I muted you before, but we have to have rules here, so you can't just speak when you feel like it. I'm interested in this gap between what, and I'm just going to put you on the spot, Mike, as being the industry and our speakers here, the academics. There seems to be quite a mismatch between the information that is available. And we heard that actually repeatedly also in the process of the review of this paper, which went through peer review as is custom for scientific publication. One of the reviewers pointed out that this information was available, but not publicly. And that, of course, is a very difficult situation. Olwenn, maybe you want to comment on that?
Yeah, this is a snapshot of what we know and what is publicly available. So we can't possibly or ethically comment on data that supposedly exists but we can't see. That is an issue. I think that's what's part of the key actions. There's probably is a lot of industry data that is available, and it would be very valuable if actually they were made publicly available so that they could be scrutinized. And unfortunately, that's not the case. So that can't be included in that analysis.
So maybe we can switch back to Emmanuel here again from EFSA. What are EFSA's plans to make this information available?
To the best of my knowledge, this information they are covered by certain confidentiality issues. So I'm not sure that they can be publicly available. Many of these things can be confidential. So I'm not really sure on this. It's a matter of decisions in the future.
Mm-hmm. Okay, but I mean, I think that's one conclusion we can draw here. That's a problem.
But this is not a problem that happens now. The problem happens since many years. So it's accumulated problem accumulating problem, in my opinion. So this knowledge, I agree fully with the comment before that this data can be somehow available, even from the industry somehow, not in a complete view, in order to scrutinize, to just lift all the potential comments or questions.
Mm-hmm. Okay, well, thank you for that. Thank you for everyone for joining us today. We could have discussed much longer, but in the interest of time, people are already signing off. I would like to end the webinar. So thanks to the speakers and to all of you participants for your questions, comments, for your interest.